perfect. Parabolic cylinder. So this is a parabolic cylinder. So when you actually make the contour diagram for this, that allows you to make some key assumptions. So first of all, your contour diagram is the edges of the shapes you get when you slice with a big sword. You have this big laser, you slice parallel to the XY plane. So it's all equations that look like z equals something else, z equals something else, and you look at the edges. So one thing you can do, which is great, you could clip this out or take a picture, put it into your notes. I highly recommend at the beginning, when you're first doing these contour diagrams, actually draw the slices. So if I drew a slice here, it's going to cut right there. It's going to cut right back there. Comes back like that. So those two red lines then get thrown down to the XY plane, and then you have another cut. All of these cuts are going to be parallel to which plane? All of these cuts are going to be parallel to which plane? The which plane? Not the XY plane, the YZ plane. So all of these right here are parallel to the YZ plane. So another way to say that, we're going to eliminate the z-axis when we do our contour diagram, right? Because we're looking straight down on the z-axis. If you're looking straight down on the z-axis, do you see the z-axis? No, it's just a dot. It's the origin. So when you're doing this contour diagram, first of all, you get to go back to the safe space of two-dimensionality, which you probably like a whole lot more now. What axis goes up on your contour diagram? Y. And what goes to the right on your contour diagram? X. We have to standardize this or it becomes impossible for us to have a conversation about it. Just visualizing this stuff full stop can be hard, but then changing perspective and talking about it, it's real hard. My lines right there aren't drawn super well because theoretically if these are all parallel, it's going to be like these, like this. Okay, so when you do this, you know that they're all going to be parallel to which axis over here? Which axis are all? The y-axis, exactly. So if we just arbitrarily choose one of them to start with, let's say we started with this one right here, what has to exist on the other side the exact same distance away? The same thing, because if this is a hyperbolic parabola, one thing we could assume is that it's going to be, what's that word within it? Symmetric, exactly. So if we arbitrarily started with that distance, you have to start somewhere. What do we know about all of the other lines? They are all going to be what in relation to those? Parallel. They're going to be parallel. The one thing, though, is a parabola, is it flat? Does it stay the same slope? No. What does it do? It gets what? It gets steeper. It gets steeper. So what does that mean about the distance between these parallel lines? They get closer together. It gets smaller. Exactly. So if the next one's like this, what does the next one do? They get closer and closer together. I'm doing it kind of gradually, but it should be a little better than that. It is symmetric. So also there's one line that's right in the middle, which is going to overlap with which one? The y-axis. So I'm just doing it in green so you can see it. But the idea is if you looked at it from the top, it looks like this. Now, do they give you values of the heights? Do they give you z-values? No. So you're not going to write it in. It's kind of hard to say, though, because if you have no z-values of this, what could this represent? It could represent a cubic curve, right? It could represent up, or it could represent down. You don't know unless you had some values. Also, actually, to be fair, it could represent a lot of different things, because what happens if this was like 10, 5, 3, -2, 8? It could be like going berserk, right? So you need those z-values to staple these contour lines to a certain height. So you could, say they're going down, but that's the idea. They want you to understand the general shape right now. The general shape right now. Ah, nice. Math puns. All right. So you need to actually pick output values. What's one great output value to start with? 0. Start with 0, if you can. So 0 equals x squared plus 2y squared. What does that mean the contour is at that specific space? What's the only time x squared plus 2y squared equals 0? 0, 0. 0, 0. Because x squared and y squared are both positive, you can't add them together and get 0 unless they are both 0 already. Okay, what's the next value you want to test? 1. So what do you have? 1 is equal to x squared plus 2y squared, and then the next one might be 2 is equal to x squared plus 2y squared. You might be asking yourself, how do I graph these? Well, what shape are all of these? They're not circles. They're ellipses. That's correct. So when you're drawing these, I'll draw the axes like this. Doesn't really matter. What's our first contour? It's a really simple one. What's the first thing we found? Yeah, so our first contour is right, let's just say right there. And I'm not going to use, that's too thick. So if I use that as my starting point, great, that's nice. How do you go about graphing this one? What's the easiest way? You know, if I told you that's an ellipse, what's the easiest way to graph that? Well, we like to connect the dots, right? So what should we find? Intercepts, right. Okay, when y is 0 on number 1 here, when y is 0, what's x? 1. What, or? -1. 1 or -1. So let's say that's -1 and that's 1. When x is 0, what's y? The square root of 1/2, so root 2 over 2. So what do we, it's a little bit more than a half, right? So it's maybe up here and down here. So this is root 2 and this is -root 2. So those are the actual, those are the actual y values and x values. So what do you do with these now? You connect them. And sorry about that curve. What height, though, is represented there? What's the height at that point? It's the z value, which is 1. So the height there is 1. What's the height in the center? 0. So it goes from 0 to 1. You need to do this one more time at least one more time. So for 2, if x is 0, what's y? If x is 0, what's y on the next one? If x is 0, what's y? 1 or -1. So you know the y values are now up here and down there. We now have 1 and -1. What about the x values? What's the x value become? Plus or minus root 2. Plus or minus root 2. 1.414, so a little less than 1.5. So it's like here and here, something like that. So what do you do with those values now? You connect them into a really poor oval that Mr. Seamon is suffering through right now. Okay. And what's the value there? 2. Yeah, those ovals are not the best right there. Sorry about that.
Isn't root 2 greater than 1?
Root 2, it is greater than 1. That's why it's to the left over here and to the right over there.
On the y-axis.
Is root 2, I'm sorry. You're drawing this. These are actually all filled in smoothly right here. It goes all the way around. So the cross section here is like that. The next one is like that, right? The next one's, they keep on doing that. It's not that the surface isn't defined there. The reason they draw it like that, why do they stop drawing it like right there? So you can see the axes. They have to make some allotment for you to like see what's going on. Do you understand what I'm saying? So it does keep, that's a good question. So yes, if that was exactly what that surface was, the contour wouldn't exist. You're right, correct. Like if that was some weird like art shape, something we could 3D print. Ooh, we could print some surfaces. Be fun. I'm totally printing a hyperbolic paraboloid today. Okay. Here we go, everybody. Extension of how many pieces of information do you need to define a unique line? How many pieces of information? 2. Can be different 2. What are 2 pieces of information you could have that define a unique line in 2 dimensions? 2 points. You could have 2 points. What are 2 other things? You could, instead of 2 points, you could have 1 point and a slope. A lot of the same, right? I really like the 1 point and slope thing because if you have 1 point and slope, what form can you use? You can use point slope form and stop there because there's usually no requirement to go any further other than trying to make yourself make a small mistake. Which one's this? That's what I'm asking you right now. And they say, oh, eject, eject. No. Y minus y equals m times x naught. Or you can say 1, doesn't matter. This represents any point is x naught, y naught, and m is the slope. Any point. So let's go back and look at what we have right here. Effectively, what do you see right here? What do you see right here in the middle? What is that? What do you see? Some different variables, but what do you see? Let's look at what we have over here. We effectively have the exact same thing, but with 3 variables. There's no new mechanism here. There's no new mechanism. We're going to talk about what each value means, but instead of x naught and y naught, we have x naught, y naught, and z naught. In each instance, what's being subtracted from z? Z naught. What's being subtracted from x? X naught. So it's a direct extension. It's a direct extension. What we're going to focus on now is the difference between m and n, because effectively we now have 2 what? These are both slopes, exactly. These are both slopes. Okay, so we have to be careful about this. We have to be very, very careful. Yes?
If you don't have the slope for the z, that means the z.
What do you mean?
Well,
So if m and n are both 0, then it's
just
flat.
keep going.
Okay, yeah, sit down. The best way I know to talk about this is just to try to do one. This is the best way I know of. How many points, if I have 2 points on it, let's say there's a plane right here, and I have a point right here, and a point right there. How many lines, how many unique lines go through 2 unique points? One. There's a unique line that goes through 2 unique points. Hold your hand up like this and point at something right now. So like ready? 1, 2, and there's a 3rd point. Let's see, everybody else put your hands up. There's 3 of them. Matt, hand down. 3rd one up, right over there. So, Nate, put your hand up. There you go. Imagine there's a point in 3 dimensions at the end of each of their fingers. How many different planes can go through those 3 points? Just one. There's only one plane that goes through 3 unique points. Any 3 unique points. So you can do this, you can move them, like, do this right now. 2 points here, 1 point here, you can move it around. Do you see the plane I'm creating?
Quickly, and I run across the room.
Yeah, okay, okay, you can put your hands down. The idea though is, does it matter which 3 points I have? No. Think of it as there's invisible lines going between all the three fingertips right here. I'm just creating a triangle that's expanding in space. Does it matter which points I pick? No. Any 3 unique points define a unique plane. That's really important. But coming up with the equation is a little nuanced, but once you do it once, you'll be really happy about it. So you have to remember, what was that equation? Can someone remember what the equation was? Raise your hand and tell me what the equation was. Lauren. Z, yeah, I'm going to do it this way. I like doing it this way just to be consistent. Z minus Z naught equals
M
yep.
X minus X naught plus M Y minus Y naught.
Correct. Now, what do you think M is? It's well, I already told you it's a slope, but which slope in particular if you had to describe it? What's it being multiplied by? X. So it's going to be the slope in the x direction. So this right here is dz dx.
Oh God.
What is, let's go to purple. I'm going to purple. What's this represent right there? I like this, dz dy. So this means right here, as you move along the x-axis in the positive direction, how does the height change? Height now is not y. Height is what? Z. You're also at a point, and then you go in the y direction. How does the height change? The way you get this locked into your brain is when you're standing on the side of a mountain. It might be one steepness to go in the x direction, and it might be one steepness totally different to go in the y direction. X direction, y direction. Key thing to realize, crucial thing to realize is, keep the perspective the same and then answer this question. So let's say I'm in 3 dimensions right now. This is z, x, and y. Pick a point in space anywhere in that reality, everybody, okay? Everybody pick a point somewhere. If you move in the positive x direction, or the negative x direction, but we're going to go positive x direction. If you move in the positive x direction, could you be going up or down theoretically? You don't know what the surface looks like, right? But if you're moving parallel to the x-axis, what value of the coordinates you are walking on doesn't change? Y doesn't change. Y doesn't change because, so let's say you had a point. Let's say the point in space is right here. If you move in the x direction, you're going to be moving on this plane, which is going to be parallel to the xz plane. So you could be going up and down. If the origin is right there in the corner of the room, everybody, let's say the point I choose is right here. Everybody with me so far? If I'm going to move in the x direction, that's straight at us, right? If I'm moving in the x direction, my height might change, right? But what value isn't changing? The y value isn't changing. So when we find dz dx, what is fixed? Y must be fixed. When we do dz dy, what must be fixed? X must be fixed. X must be fixed. So what happens? So what's the equation of that plane right there? This plane right here. So let's say that point right there was 2, 3, 4. What's the equation of that plane right there? Nope.
Y is 3.
Y equals 3. That's y equals 3. So if I'm traveling on this plane, so imagine there's a surface that plane is intersecting with. If I walked along that surface in the x direction, I might get some sort of path. I'm just making it up. Let's say the path looked like this, right? Let's say this surface looked like this, okay? Everybody see the surface I'm trying to draw? This might be the path that I'm walking on, right? What is not changing? The y value. Is the x value changing? Yes, it's getting bigger. What's happening to the z value? It's getting lower. It might go up again. We don't know. I'm just making the surface up, right? What happens if I did the other one? So this right here is dz dx. But I might go to the right, so go into the y parallel to the y-axis. Everything just rotates 90 degrees. If that's the case, we wouldn't have y equals 3. We'd have x equals 2. And then your path would be going in the other direction. Why is this really important? It's really important because when you have your 3 points, sometimes, in this case in particular, they give you 3 points that really, really help you. So let's look at dz dx. Y needs to stay fixed. So if this is the first point, the second point, and the third point, which 2 points are we going to use? Which one?
1 and 3.
Y 1 and 3.
Because y is the same.
In these cases, y is the same. Y doesn't change. Y doesn't change. Nice. Okay, y doesn't change. So what does that mean the slope for, what is dz dx going to be equal to? What's the change? What's the change in z value? If we go, let's go from 1 to 3, everybody. This is 0.1 to 0.3. 1 minus what? Minus what? Minus -1. Do you see those two values, everybody? So 1 minus -1. That's the change in z. We're just doing slope at this point. What goes on the bottom? The change in x. Going from 1 to what? 3. 1 minus 3, so that's going to be what? It's going to be 2 over -2 is -1. So that right there is our what value? dz dx. Next, what do you need to do? dz dy, but that's when what is fixed? X. So instead of going from point 1 to point 3, and I'll erase these so we can do a different coloration here, we had a fixed y value right here, but now we need to look for a fixed what? X value. Where's the fixed x value? 1 and 2. So we're going, in this case right now, we're going from 1 to 2. So dz in this case, 1 to 2, is going to be 1 minus what? 1 minus 3 over what? It was 1 minus 3, and now it's y, so it's going to be 0 minus -1. So what's that going to be? -2 over 1 is, so what this right here is our dz dy. So what is our equation now going to be? Well, how many points do we have to choose from right here? 3. So how many different choices do we have for z naught, x naught, and y naught? 3. We just need to pick the, you can't interchange them. So which one do you want to use? 0.1, 0.2, or 0.3?
1.
Yeah, use 1. Why did you choose 1? It's the same one I would choose.
It's the first.
It's the first one. Numbers are positive and 0, and they're 1s. We like that, right? So what's the equation going to be? Z minus what? 1 equals, what's the dz dx? Negative x minus 1 plus, what's the n value? -2 times y minus 0. Can you clean this up a little bit? Sure, but if you write it like this, it communicates to me that you've filled in the right things in the right places. Lena, theoretically, to show that it's not on a plane. You find one error, right? You find one inconsistency. So let's say you're doing these, put the plastic down. If you do the gaps and one of them comes out differently on a row, what do you automatically know? It's not a plane. All you need is one thing that's inconsistent to show it's not a plane. So here's the written out steps. Each row and each column is linear. All the rows have the same slope and all the columns have the same slope. Although the slope of the rows and the slopes of the columns are generally different. You understand? Like it might be steeper this way than that. They're not the same in both directions. It can't, can it be? Yeah, it can be. First 3 points generally really nice to use. What's one reason they're really nice to use? Yeah, well, they're perpendicular, so that's, A, they need to be perpendicular so you can do this type of manipulation. What else?
They're integers.
Yeah, they're pretty clearly integer values. Like, don't go picking, like, this point right there. You're like, nah, don't. Pick the nice ones. when you do this out, you might have noticed also that you can pick 0, 0, 0, which is a great point to pick. You'll also sometimes see, so we see this a whole lot, z minus z naught equals m times x minus x naught plus n times y minus y naught. Well, when you get the final version, when you do it out, you generally can get it in the form of z equals ax plus by plus sometimes like plus c. When you actually do out the actual algebra, like that's another form to put it. It's like the difference between standard and general form. Generally speaking, it doesn't really matter. You might be forced, if it's multiple choice, to manipulate the two.